Okay, so for task one, first task was to read the prompt and understand the situation. So our objective is to determine the position and motion of the Aldrin planet that's under the influence of gravity. The way we're going to go about doing this is first by solving this by using ND-solve for equation 3, which is really a system of equations just labeled as equation 3. Then we're going to plot them using the initial conditions provided in parts A through E to get some sample solutions. Our second task is to solve the second order of ODEs and bring plots, but we'll just bring a Mathematica notebook with us to show our plots. As mentioned earlier, we're going to use ND-solve for this system of equations labeled equation 3. And then to better visualize the solution and to make better sense of it, we'll use parametric plot 3D to see how the planets will move under the conditions of gravity. Task 3, what could the solutions represent physically? Physically, our solutions and plots could represent the potential movements or paths or motions of the planets under the influence of gravity given the initial conditions. And then finally, discuss the conservation of energy. That's just the energy in the solution should be constant.
Alright, so for task 2, we got to write down the equation for SSE functions involving two different variables. And the way we're going to go about this is we got to determine the particular curve that planet Aldrin follows, and we want to figure out how circular or elliptical its orbit is. And to do this, we're going to find the best values for E and D of the equation of equation 2 by minimizing an SSE function, and we're going to do that in Mathematica. We'll then find what our SSE is by comparing the predicted R values to the actual R value in Excel. And so question 2, in your own words, describe Kepler's second law. And I think this is basically saying that the distance from the sun to the planet will be proportional to the time it takes to orbit a certain distance of its orbit. In other words, for a planet with a very elliptical orbit where it's very close to the sun at some point and very far from the sun at others, it will orbit faster around the sun at some points where it is closer to the sun and slower where it is farther away from the sun.
For task 3, our first question is to know what additional force do we need to consider. So previously, we've really only concerned ourselves with the force due to the star, but now we also need to worry about the force of the sun as well. Next, we need to discuss the conversion for light years. So when completing parts for task 3, we'll have to make sure to convert all quantities to light years. And the way we did is we Googled it, and we found that 1 light year is approximately equal to 5.879 e to the 11th miles. And then if we're using meters or kilometers or whatever, we can just convert miles to kilometers and then do that equation. Our next question, what makes a vector field conservative? Then reading a bit from the Stewart Calculus textbook, we know that a vector field is conservative if a vector field is the gradient of a scalar function. And then our fourth and final question for task 3 is, if we have a conservative vector field, what can we say about work and our choice of path? In essence, no matter what path we take, it will be the same amount of work, assuming, of course, that the vector field is conservative.
So our next task is going to be task 4, and the first question that we have to answer here is, in our own words, describe what is a multi-stage rocket and what is the purpose of a multi-stage rocket. So first, a multi-stage rocket is a rocket which has multiple rocket sections. By this, I mean the rocket itself has several rocket boosters contained at different places along or in the rocket. The purpose of this is that when one rocket or set of rocket boosters has exhausted all of its fuel, that section can be jettisoned from the rocket. The next rocket or set of rocket boosters will then ignite, and the rocket will have significantly less weight. And question 2, what technique will you use to minimize the total mass of the rocket? Drawing from our skills learned in MA 153, we will use Lagrange multipliers to minimize the total mass of the rocket.
Yeah, I think that's by and large it. Thank you, and we look forward to reading your questions or comments.